Dear all, welcome to a new video relating to entropy and thermodynamics. Today we will talk about entropy and information. So last last time we had some discussion about entropy. So we actually derived a relationship about entropy that was minus kb sum over I pi log of pi, and I did not mention the name of this kind of entropy. This is known as Gibbs entropy formula. And before that we actually derived another formula that was kb log of omega, and that was Boltzmann's entropy. So today we will take both of these into account, and we will connect this thing to information. We will define what is information before doing anything, and then we will try to connect these formulas with information, and we will try to see what entropy actually means and how we can interpret it in a different way from what we interpreted last time. So let's get started. So first we define what is information. So information is basically any meaningful stuff. So I give you here an example. So here I give you three different statements, and you judge for yourself what they mean and how much information they contain. So I give you first statement. Albert Einstein Albert Einstein's birthday falls on a particular day of any year. So you see that how much information I have given you from normal day-to-day perception. You say, okay, so your answer most probably will be no information. Because we have 365 days for a normal year. So how can we say, okay, which day is that? It can be any day. And if we calculate probability, okay, so we are assuming here that you don't know about the actual birthday of Albert Einstein beforehand. So this is the first statement that you got for this. So what we do, so we simply calculate probability from this information. Probability of birthday of Albert Einstein. So we see that it is equal to 365 over 365, that is 1. So we had no other information, and we don't know anything else about that day. So we just take this statement and convert this tell we say that okay, this is the only information we had, and we normally call this no information. Okay, so normally this is a ridiculous statement, so you'll say okay, there is no information, and then you calculate probability out of this, that is 1, the maximum probability we had for this. Okay, now I go to the another statement, statement number 2, and I give another statement. So that is Einstein's birthday falls in the first half of the year. And you should judge this with respect to information that I'm providing. So if you ask yourselves, so you'll say okay, we have now some better information. Okay, still it's a nonsense information, but you say okay, it is somehow better information, but not so valuable. Okay, not so valuable. Okay, so half of an year is okay, still half of the time, and it contains half of 365 days. Okay, so 183 days, and we cannot pinpoint so easily which day it could be. Okay, we say okay, it is from January 1st to June 31st, but which day we don't know. So we somehow we want to we are concerned with probability, so we calculate probability for this statement. So the probability in this case would be, so there are 6 months out of total 12 months, so we say okay, this time the probability is 6 over 12, so it can be any of the 6 months out of 12 months. So now we have a probability of 1/2. So our probability has decreased. Information somehow increased, probability decreased from 1 to 1/2. Now I go on to tell you the third statement, that is Einstein's birthday falls on 14th of a month. So now the information is becoming more specific. Okay, it's not like a complete information. I'm not giving you the exact month of Albert Einstein birthday. Okay, but I'm telling you that okay, we have now the birthday falls on 14th of a month. So how much information? Okay, bit more information than the previous statement, and you should not take two statements together for the time being. So there are three, they are three independent statements. तीनों statements को आपने differently treat करना है. आपने यही समझना है कि एक वक्त में आपको सिर्फ वही statement पता है. So then we calculate probability. So how many 14th in a complete year? How many days they make when you count the 14th of months? So there are actually 12 days, 14th of January, 14th of February, and so on until December, and you have 365 days overall. So I should use the, for information I should say more than what statement 2 provided us. Probability, birthday. So there are 12 days of 14th, so 12 over 365, and we have now 0.03. So we see that with each newer statement with better information content, our probability is successfully continuously decreasing. So that is the relationship between probability and information from like this simple example. So probability, we can give a statement is inversely proportional to the information that we have, and this information, okay, so we are treating the information independently. We write this, okay, independent information. We are not taking two statements together. What happens if we take two statements together? Will the probability increase or decrease? Okay, I leave a small assignment for you to judge. Okay, if we take these two statements, statement number 2 and statement number 3 together, what would happen in that case? And I go on to explore this relationship between information and probability further. So as I told you that these information and probability are inversely related, so we can write a statement, what we call this quantity. How do we quantify the information in some statement? We call this quantity of information, and quantity of information we call this Q is equal to minus K log of P this is the definition of quantity of information. This definition was provided by Shannon. Shannon was a scientist. Okay, we don't need to go into details of who Shannon was, but okay, that's the statement, Shannon's definition. Okay. Here K is not actually Boltzmann's constant, it's just a constant, another constant. You can call it Shannon constant, just a constant, and P is probability. And this minus sign takes care of the inverse relationship here between information and probability. Okay, so if we have an event with I outcomes, so information content, yeah, or information quantity in any of these outcomes is Qi, that is minus K log of Pi. Okay, so last time we showed you how to calculate average value of a quantity. So now if we want to calculate the average of information content. So we write, okay, Qi or Q, simply Q, that is sum over I, Qi Pi over sum over I Pi, and this quantity I told you last time in the denominator is always equal to 1. So we write average information as sum over I Qi Pi. So, and okay, so I should write this the statement which I gave Qi. We call this equation 1, and average value of information we call this equation 2, and if we put Qi in equation 2, we get average Q equals, put 1 into, so we get minus K sum over I Pi log of Pi. So if you remember, this looks similar to the Gibbs entropy that we calculated. So this is another kind of entropy, but here, okay, in Gibbs entropy we used here Boltzmann constant. Here we are using some other constant, so we call this thing as entropy. But which entropy? Shannon's entropy. That is minus K sum over I Pi log of Pi, and okay, you can call this equation 3. So now we are in a good position to see, okay, what is the relationship between Shannon's entropy and probability to the Gibbs entropy or to the Boltzmann's entropy, because they are related to somehow systems with some microstates available to them, and this Shannon's entropy is related to information content of a system. So we further explore it, what that means. But okay, so I should write first this equation 3 in simple words. So the average information in a system is called Shannon's entropy. And remember that this was derived from direct probability, and it has no connection with thermodynamics or statistical physics as such. So we will now make a connection between the two. And before making that connection, okay, so I should do one example to make this thing clear, what this Shannon entropy stands for in terms of information. So example is, suppose we have a fair die, fair 6-sided dice. So we make a table of outcomes and their related probabilities. And their Q. Okay, so it's a fair six-sided die, so it has outcomes 1, 2, 3, 4, 5, and 6. And we know that the probability is associated with each side because it's a fair die. We write it, okay, 1/6 each. And the Q we calculate from Q equals our equation 1. So we calculate Q from our equation 1. We put each value of PI and then we calculate Q, and what we get, K log of 6, K log of 6, and 6 such statements of K log of 6. And there is a tradition that here we may take K equals 1 and use log of basis 2, and we calculate log 2 of 6, and we get this information in terms of bits. You know this bits concept 1001. So actually we can for sure use this as our understanding purposes. So now we write Q in bits. So we see that each bit is 2.58. K log of 6 here is 2.58, 2.58, and for each of these is this value is 2.58. And if each value is 2.58, what is average Q then? That is also 2.58 average Q, or you can call it as Shannon. That is 2.58 bits. The unit is bits because we have used log 2 and K equal to 1. So we have average information in this type of numbers 0 and 1, and 1/6 probability means information of 2.58 bits. So we take an alternate die. So let's take another die. But a biased one. Meaning that it has one side a bit heavy, so we have different probabilities of each side. So in the last example we took, okay, each side has 1/6 probability. This time we take, okay, it has different probabilities of each side. So some sides have lower probability, and one of these sides, due to its weight distribution or mass distribution, its one side is heavier, so it has more probability of getting up. So it can be made, actually. You should know that we can make unfair or biased dies. So this time we make another table. So we write, okay, outcomes, probabilities. So outcomes are still the same, 6 outcomes, 2, 3, 4, 5, and 6. However, we have different probabilities this time. So this has 1/10, but sixth side has higher probability. We call this, okay, we say this has a probability of 1/2 because it's an unfair die. Okay, you should remember always what we are doing. So now we calculate Q. So that is K log of 10, K log of 10, so on, and in the last we write k log of 2 because of different probability here. And now we calculate q in bits by using log of 2 to the base 2 and k equal to 1. So this time we have the information, this has 3.32 bits. Wherever we have k log 10 we have 3.32 bits, and where we have the k log 2 in one of those outcomes, so there we get k log 2 equal to 1 bit. We have 1 bit here at the last outcome. What is the average? Average Q, or Shannon's entropy. So you just add all of these 6 and divide by 6, and what we get, average value we have now, Q average is 2.16 bits. So this Q, average Q or Shannon's entropy, for, I write this, okay, so that you should be clear. So Shannon's entropy for biased dice is less than Shannon's entropy for a fair dice. You see, I just rolled back here. So here we have 2.58 bits on the average, and here we have 2.16 bits on the average. So that's the scenario. So how to interpret this, what that means physically, what do you understand about this? So to understand this, we say that okay, so we should go back to probability and see what probability means. So probability means how likely an outcome or set of outcomes is. So if we have some given information and we want to predict something about it, okay, so we have some information and we want to predict something, we say okay, so this thing will happen for sure and the other thing will happen, okay, we are confused about it. So our Shannon's entropy actually as Shannon is proportional to our uncertainty in a statement or set of statements. How? So for example, in case of a fair dice, we had Shannon entropy smaller, and for a biased dice we have a higher Shannon entropy. So we say that we had a higher uncertainty for a fair dice. So all of its 6 outcomes are equally likely, so we are all the time confused which side would be up. Okay, so we were all the time confused or uncertain that if we throw the dice, or which outcome we will get. We will get a 1, 2, 3 or 6, we never know. But if we made a dice biased one or unfair one, we somehow manipulated it. So now this time we are sure that we have more chance of getting a 6 and we have less chance of getting any other number. So we are more certain. That's how Shannon entropy works. So Shannon entropy is directly proportional to the uncertainty in some experiment or in some outcome. Whenever we have a higher Shannon's entropy, means we have higher uncertainty in that. That is why, okay, I repeat, that is why a fair dice has more Shannon's entropy, and a biased or unfair dice has less Shannon's entropy. Very good. I hope you got some idea of this certainty, uncertainty, and Shannon's entropy. Now we apply this to our previously known entropies of Gibbs form or Boltzmann's form, and we see, okay, what how this connects to thermodynamic and statistical entropies. So we call this topic as information in thermodynamics. So imagine system. We have a computer. We have a computing device. And a large heat reservoir. Joined together. So that's what we are actually wanting to establish. We want to establish a relationship between information and thermodynamics. So information is, okay, our computing device, it contains some information, and heat reservoir is our thermodynamic entity. So we just draw a simple block diagram. So we have a PC in which we have some information, and we have somehow large heat reservoir. So suppose, also we have to suppose another thing. Suppose the PC, personal computer, is it has, suppose the PC has n bits stored in it. What that means, okay, so you all know somehow that how information is stored on our computer. So it is in the form of specific sequences of 1 and zeros. So 1 0 1 1 0 1 0 0 1. So some sequence of this bits. So I don't know how many are these or how big is this n, but it is a PC, so it may be a very large number. So how much entropy is associated with it, this system? Entropy associated with the PC. So we use this old formula for our entropy, that was Boltzmann's formula. S is equal to kV log of omega, and omega is proportional to, so bits has only two types, so 1 and 0. So we use 2 here, and we have n bits, so it should be raised to the power n. How many bits? How many number of states? How many number of arrangements? We studied this in our couple of lectures ago. So okay, so we use this omega equal to the power n, and we just plug it in. S equals kV log of omega, kV log of 2 to the power n or n kb log of 2. This is the total entropy. Entropy associated with PC. And now suppose we want to erase this information. Just we want to store some other information, and before storing that other information we want to just erase this previous information. So what we do, so suppose we want to erase the information from the PC. So how do we erase information? So you know that, okay, we can set all the bits to 0. We say, okay, by some method with the sequence of bits, all of the bits equal to 0, then the information is lost. That means we have erased the information. Or we can set all the bits to 1, because information is a special sequence of bits, and if all the bits are 0 or all the bits are 1, then there is no information anymore. So we say, okay, after we erased, after erasure, the entropy associated with the PC is S after erasure. So if we set everything equal to 1, any one of these, I mean we don't use two of the at the same time, so we use either all zeros or all ones. So in any case, if we have all zeros, there is no sequence, there is only one state there. There are not so n 2 to the power n states anymore. So we have all the zeros, no difference between any zero, so this is called only one state. So now we write S is equal to kb log of 1, because we are left with just one micro or macro state, whatever you call it, and this is the entropy. Okay, log of 1 is 0, so that we have 0 entropy. So there is a net decrease in the entropy. So there is a decrease in the entropy of our PC. How much is the decrease? So we calculate ds. That is equal to S after erasure minus S before erasure. So 0 minus n kp log 2, so minus n kp log of 2, ln of 2 or log of 2, you can use any of these for the timing. So decrease in entropy, somehow we are not satisfied with this kind of statement. So we have known from the thermodynamics laws that entropy, change in entropy, is always greater than or equal to 0. that we know from thermodynamics, that we emphasized too much when we were studying thermodynamics a while ago. So what is the matter? So we go back to our model system where we had our PC connected to the heat reservoir, and we see, okay, this much change in entropy produced how much heat in the PC. Heat produced in the PC due to erasure. So we should use the formula for the change of entropy, TQ over T, and we modify it equal to TQ equals TdS, and we put the value of ds here. So dq we write minus n kBT log of 2. So minus sign signifies here that this much heat is generated, and this much heat should be transferred to where? To the heat reservoir. This much heat needed to be transferred so this much heat needed to be transferred to the reservoir. Why? So that net change in the entropy of the composite system becomes 0. So that was it. So we learned today that what is information content. Summary for today is so we write we learned information content and its relationship to probability entropy and thermodynamics. Next time we will learn more about probability distribution functions, and we will start with binomial distribution that you are somehow not familiar with, and we will study this binomial distribution in a bit more detail. You actually tried to use this binomial distribution in the last assignment, which was totally unexpected. So I hope you will learn this probability distribution before you use it next time. Thanks.